Professor Dave and Chegg here. Now that we understand the way the equilibria operate, and that if a system is not at equilibrium, concentrations will change until they reach their equilibrium concentrations, it is time to learn how to make calculations regarding these concentrations. This is probably the area of general chemistry that is the most mathematically involved, so some students will find such calculations to be tedious. But they are important, so let's make sure we are prepared for them.
The first thing we must recall is that at equilibrium, the reaction quotient is equal to the equilibrium constant. This means we will have a value, K, to plug in for Q in this expression. But if a system is not at equilibrium, we know that concentrations will increase or decrease until the system reaches equilibrium. And the concentration of each substance will shift in such a way that is in accordance with the stoichiometry of the reaction. This means we can do algebra to figure out the relative changes in concentration for each substance. Let's use the decomposition of ammonia as an example. Let's say we start with some amount of ammonia and allow it to decompose. We want to be able to keep track of all the concentrations as they change. As a result of the decomposition, the nitrogen concentration increases by 0.11 molar. What would be the increase in hydrogen concentration? Well, according to these coefficients of 1 and 3, with every nitrogen molecule that forms, 3 hydrogen molecules form. That means whatever the change in concentration for nitrogen, hydrogen concentration will change triple that amount. So we can multiply 0.11 by 3 and see that hydrogen concentration will increase by 0.33 molar. Likewise, for every molecule of nitrogen that forms, 2 molecules of ammonia have to decompose due to this 2-to-1 ratio, so ammonia concentration will change twice as fast as nitrogen concentration changes, and with opposite sign. So in order for nitrogen concentration to increase by 0.11 molar, ammonia concentration must have decreased by 0.22 molar. Now, let's instead say that we did not know any specific numbers. We could still discuss relative changes in concentrations by doing algebra. Instead of saying 0.11 molar for nitrogen, let's just say X. Then the change for hydrogen would be 3x, and the change for ammonia would be negative 2x. So as you can see, all we are doing is applying the stoichiometry of the reaction. Now that we know how to assign these terms, we are ready to learn how to calculate parameters of an equilibrium algebraically. The most basic calculation we can do is to calculate K given the equilibrium concentrations of all the substances involved, or similarly to calculate a missing equilibrium concentration given K and the other equilibrium concentrations. Let's try each of these now. First, let's calculate K, perhaps for the decomposition of ammonia. This is quite simple because we already know how to write the equilibrium constant expression, which is the same as the reaction quotient expression. That would look like this. If we happen to know all these concentration values from experimental data, we would simply plug them into this expression to calculate K. But sometimes we may have to calculate one or more of these concentrations. To do this, we must learn how to use an icebox. For these, ICE stands for Initial, Change, and Equilibrium, which represents the initial concentration of each substance, the change in concentration, and the equilibrium concentration. Let's see how we can construct an icebox for the following equilibrium if we are given these initial concentrations. First, let's construct the icebox with rows for initial, change, and equilibrium. Then we can plug our initial concentrations into the first row here. The reactants were given, and there isn't any product at first, so that will be 0. We learned how to assign variables for the second row already. We do this according to the stoichiometry. If x is the increase in product, since some of that must form, minus x will be the change in each reactant, because it is a 1-to-1-to-1 ratio for these substances. We add initial and change to get equilibrium concentrations. But beyond the algebra, we also know the equilibrium concentration of I2. So if we set this expression equal to that value, that will allow us to solve for x, which in turn allows us to assign all the equilibrium concentrations. Now we just plug all these values into the reaction quotient expression and do the arithmetic to get K, which will be 776. So as we can see, if we are given all the equilibrium concentrations, or a way to find all the equilibrium concentrations, we simply plug them into this expression to calculate Kc for any equilibrium. What if instead we already know K and want to use this to calculate one of the equilibrium concentrations that we don't know? To do this, we can take the K value and other known concentrations and plug them into this expression. Take, for example, the following equilibrium. Let's say we know the following value for K, and we also know the equilibrium concentrations of nitrogen and oxygen. What will be the equilibrium concentration of NO? First, we must certainly be able to write the correct reaction quotient expression. This will be NO concentration squared, because of the molar coefficient of 2, over nitrogen concentration times oxygen concentration. Then we can rearrange this to solve for NO concentration. We simply have to bring the reactant concentrations up to the other side, and then take the square root of both sides. Now we are ready to simply plug in all the values we know and do the arithmetic, and this should be the equilibrium concentration of NO, 3.6 times 10 to the negative 4. Let's try another. For this equilibrium, here is the K value as well as the equilibrium concentrations for nitrogen and hydrogen. What will be the equilibrium concentration of ammonia? Well, let's first write the correct expression. Then we will need to solve for ammonia concentration, so let's rearrange and take the square root. Then we can plug in what we know, and 1.53 molar is what we should get. Again, if we must do some algebra to attain one or more concentrations, we will simply consult the stoichiometric ratio. Now let's learn how to calculate equilibrium concentrations given some non-equilibrium concentrations and the K. To do this, we will need to follow 4 steps. First, we need to know the direction in which the equilibrium will move in order to equilibrate. We can do this by comparing Q to K. If Q is smaller, it will move to generate products. If Q is larger, it will move to generate reactants. This is important because we need to know which substances are going to decrease in concentration and which will increase in concentration in order to do the math correctly. Next, we can algebraically determine the relative changes needed to reach equilibrium, which we have learned how to do, like for this equilibrium where the stoichiometry dictates that as 1 mole of each reactant is used up, 1 mole of product is generated. We can then plug initial concentrations and the algebraic relative changes into an icebox to find the equilibrium concentrations, whatever those might be. Next, we solve for the equilibrium concentrations by plugging these algebraic terms into the equilibrium constant expression and solving for x, which allows us to get quantitative answers for all of the equilibrium concentrations involved. Lastly, we might check our arithmetic by plugging our answers into the expression and making sure it gives us the K we would expect. Let's say, for example, we are looking at this equilibrium. Given the following K and initial concentration of PCl5, what are the equilibrium concentrations for all the substances? Well, let's build up our icebox. We know that these are our initial concentrations. For the change in concentration, since there is only reactant to start, we will be moving in the forward direction, so PCl5 will be decreased by x, and both the products will increase by x. This is due to the stoichiometry of the equation. From these, we can write the equilibrium concentrations as follows. Now we plug all of these into the equilibrium constant expression and see what we get. So looking at the expression, let's put in everything we have, the K, x for the 2 products, and 1.2 minus x for the reactant. Now we just do some algebra. Let's multiply both sides by this denominator, and then distribute this number across the parenthetical. Then let's just get everything on one side and equal to 0. That leads to this equation. Remembering our basic algebra, we can factor this to give x plus 0.4 times x minus 0.3, which means the solutions for x are negative 0.4 and positive 0.3. Since the negative value would give nonsensical results, as we can't have negative amounts of substances, let's take the positive value and plug it into our existing expressions for the equilibrium values, and these are what we will get.
But with some more practice, it will become intuitive, such that you will be able to do many calculations with equilibrium expressions. Professor Dave for Chegg. See you next time.